Okay, hello everyone. Good afternoon. So, as Rick mentioned, I'm Chunandra Sahu. I'm currently an assistant professor here at IIT Kanpur, and I have fluid mechanics and heat transfer background, and that is what I will be talking about. So, I believe most of you are familiar with heat transfer. At least you have some knowledge of it. You are not completely novice. So, we will be actually starting with the motivation of why we study heat transfer. Okay, so there's the need for thermal management. We'll very quickly talk about it, and then we will go talking about modes of heat transfer, right? How does the heat transfer happen? What are different modes? And I believe this is where you have some knowledge, but again I will be covering all the basic things, so you will be able to catch very quickly. And once that part is done, we will talk about numerical methods that many times we use in solving heat transfer problems. And obviously, numerical methods are something that you can do using very basic equations, and also you can do very complicated computational modeling. Like, for example, you use ANSYS software, etc., for heat transfer. So we will do very basic uh, uh, numerical model that at least will give you a sense of how it is done without going into the full details. Okay, and then we will do one example in MATLAB. So we will see once we do the coding or once we do the numerical discretization, how we can write a code in MATLAB for that. Okay, so we will try to finish everything in 1 hour, or it might go up to 1 hour 15 minutes or 20 more minutes. So we will see. Okay, so let's start with this. So this is something I don't need to discuss much because I'm sure you all know. Like in most of the electronic parts, let's say let it be computer or any uh, other electronic machine in any industry or office or anywhere, they all have some heating components which increases the temperature of the complete body, and that's why you will see the CPU attached to the computer. Let it be in a laptop or in CPU, or so you will have a fan, right, that tries to cool it down. And why we do it? Because most of the electronic failures happen because of the failed thermal management, because of the high temperature, right? And that is what this chart says. So most of the electronic failures happens because of the uh, temperature, high temperature, and only 45% comes from either humidity or dust or vibration. We give a lot of importance to, for example, dust. We try to clean our laptop clean all the time, right? But that doesn't really matter much. That just adds to 6%, and that's why it's very important to do thermal management precisely if you want long lasting electronic item. Okay, so having covered that basics, let's go into how does heat transfer happen, or what does how does this failure happen? Okay, so, and to understand that, we need to understand the basics of heat transfer or modes of heat transfer. So let's start with that. Different modes of heat transfer. So you might have already realized I do not have a very good handwriting, so you will have to bear with that. But I'll try to do my best to write it clearly. Okay, so different modes of heat transfer counts. First one is conduction, right? And then second one is convection, and third one is radiation. Okay, so conduction happens without moving anything. So it can happen in solid, it can happen in liquid, it can happen in gas, right? But for convection, we need something to move. For example, when water moves, convection happens. When air flow, convection happens. So convection can't happen in solid. It can happen only in liquid or gas. So collectively, we can also call in fluid, right? And radiation can happen anywhere. It doesn't need a medium. It can happen without actually having to go through liquid or gas. However, for today's lecture, we will cover only these two topics, convection and conduction. Okay, and then we will take an example where both concepts of conduction and convection are included. Okay, so let's start with conduction. We will discuss this in little more detail. So let's assume that there is a solid, okay, some solid. It can be some iron piece or steel piece or something like that. So at one end, if it has 20 degrees temperature, in other end, it has 100 degrees Celsius temperature. What happens? There is a heat flow from right to the left, right? In that heat flow is written as Q. So Q is actually proportional to, let's call it T hot, and in this is called Tc, that's T cold. So Th minus Tc, right? So it's proportional to the temperature difference. And it is also proportional to the area through which it is crossing. So let's say this is the cross-sectional area. So area, Th minus Tc. And at the same time, it is also proportional to the length, because that brings the gradient, right? So Q is proportional to area, Th minus Tc by length. In this thing collectively, we can convert into gradient. So this is basically a gradient, not just the temperature difference. So we can write it as T dt by dx, right? And now if you remove this part, that gives us a constant of proportionality. So that tells us K A dt by dx. And why we put minus? Because temperature, heat transfer always happens from higher temperature to lower temperature, where this gradient is already negative, right? So this is called thermal conductivity. Right, and that has a unit of watt per meter Kelvin. Okay, A here is area through which heat transfer is taking place, and this is temperature gradient, right? So this is a very simple example where we considered one just block of solid where there is high temperature at one end and low temperature at the other end, and this is a simple heat transfer model. But what happens if in the beginning, let's say, so in this example we assume that these two ends are at this temperature already from the beginning, but let's assume that initially this block of solid was at 20 degree here as well as 20 degree here, but all of a sudden we now, this is still 20 degree, and we make this part 100 degree. Okay, we give some heat through let's say electric coil, it becomes 100 degrees Celsius. What will happen now? It will start transferring heat, but at the same time, the temperature will slowly rise, right? In after, let's say after 1 minute, if we call this is T mean, Tm. So Tm could be after 1 minute, it could be maybe 30 degrees Celsius. After 2 minutes, it could be 40 degrees Celsius, right? After 10 minutes, it could be equal to maybe 90 degrees Celsius. So this temperature is actually changing with time, right? Or this gradient, what we saw, the temperature gradient, it will look something like this here. It may be something like this, where it is 20 degree here, 100 degree here. So this one, the straight line that you see is at the asymptotic after a long time. But once you start giving heat, this actually, earlier it was 20 degrees. So slowly it actually increases like this, right? So this change in temperature, that's transient temperature, right? That we need to use a separate equation. We can't simply use this equation that we discussed, the first equation here, right? By the way, this is called Fourier's law. Fourier's law of heat conduction. Okay. All right. So now we have to consider the transient effect, and to consider the transient effect, or it's also called unsteady state, unsteady effect. So if you have to consider the transient effects, we need to consider transient equation, or in heat equation, that we generally call it heat equation, and that can be written as dT by dt, where capital T is temperature, small t is time, okay, and it is proportional to d square t by dx square, okay. And what is x? X, let's say this coordinate, sorry, I should put it this way, this horizontal coordinate, right, or the longitudinal coordinate through which heat transfer is taking place. So this is when we have to consider the transient effect, because this t, small t, that tells us how temperature is changing with time, okay, and this is called heat equation, okay. And in this case, what we see is we have temperature, time, and x is distance, but we also have a term called alpha, okay, and that is known as thermal diffusivity, okay. This is little different from thermal conductivity. Thermal conductivity we saw before in equation in Fourier's law, where alpha is actually k by rho Cp, if I'm not wrong. It should be k by rho Cp, where Cp is specific heat and rho is density, okay. So we need at least two parameters to be able to model heat transfer. If it is like when you are modeling it at asymptotic state, we need k, that is thermal conductivity. When we are modeling it for transient state, we need alpha, and that is diffusivity, thermal diffusivity, okay. So this is what we have in one dimensional case, one dimensional heat transfer. Now let's assume that you have a block of solid which is three-dimensional in nature. So this is your block that looks something like this, okay. All right, and this is x direction, this is z direction, and this is y direction, okay. And now in the beginning everything was, so Ti, that's initial temperature, was 20 degrees Celsius everywhere, okay. Now all of a sudden you started heating one part of it, so this red circle in the bottom, that becomes Th is equal to 100 degrees Celsius, let's say, all of a sudden, okay. And now it starts dissipating heat in all direction, okay. So it's dissipating heat in all three directions, and you want to calculate the temperature, for example, somewhere here, okay. And now because you are supplying heat only from a point here, if you want to calculate temperature, let's say on the top surface, on this surface, temperature may somewhere here, for example at the center or the left here, they all may be different, right? So let's say this is 0.1, this is 0.2, this is 0.3, this is 0.4, and this is 0.5. Now because this is not uniform, you are supplying heat from one single point, and that's why if we number them as T1, T2, T3, so T1 may not be equal to T2, it may not be equal to T3, and this is why you need to consider heat transfer modeling in three-dimensional, okay, or conduction, heat conduction in three dimension. And for that we need to extend the equation that we saw before, that transient heat equation, as alpha d square T by dx square plus d square T by dy square plus d square T by dz square. So this equation will give you heat transfer uh, rate in different directions. Okay, and just this one equation is not enough. Obviously, you will have to apply boundary conditions, initial conditions, which we will discuss when we take an example. Okay, so this is one equation you have, and you should note this equation. Now let's go. We will talk about convection. Let's go to another page. Okay, so conduction happens only in solid. I mean, sorry, is there any question? Okay, so conduction happens in solid, liquid, or gas, but without any moment. Okay, it happens just with static fluid, static gas, static solid. But convection happens with motion. It doesn't happen with static fluid or gas. So let's consider an example. Let's say this is the wall, okay, wall outside your home or inside your room, etc., and it has some temperature. Let's say this hot. So this is outside of your room, this is inside of your room. Okay, so room temperature inside is 20 degrees Celsius, and it is summer, so temperature outside, let's say, is 40 degrees Celsius. So this heats up the wall, and when wall gets heated up, that is also 40 degrees Celsius now. Okay, now it starts emitting heat, right? Or it starts transmitting heat to air. So what it will do, it will heat the air in this region, and that air will now starts moving up because of buoyancy, right? So what happens here? So when air gets heated up, it starts flowing because of that extra buoyancy it has got, or the reduced density, right? So this moment that happens, that is basically convection, or the heat transfer, amount of heat transfer that happens from this wall to air. So from solid to liquid due to fluid motion is actually called convection, right? And here also we can calculate the amount of heat transfer, and this amount of heat transfer is proportional to T, let's say we call T wall, TWST wall. So T wall minus T air, right? It will be proportional to the temperature difference, and it is also proportional to the area. Okay, so if area is, let's say, 5 meters square, then there will be more heat transfer. Obviously, if it is just 1 meter square, then less heat transfer, etc. All right, and now if we convert it into constant of proportionality, it gives us HA delta T. So delta T is this part. Okay, and H here is called heat transfer coefficient. Okay, so in contrast to what we saw before, we had seen K, right? That was thermal conductivity. So thermal conductivity is actually material property. It's a material property, and it of course depends on the temperature, but it depends on the material. Whereas H here, heat transfer coefficient, that doesn't depend just on the material, but it actually depends on the flow conditions and rough wall roughness and many other things. Okay, and that's why H is actually variable, and it depends on the several things, for example, flow conditions, etc. And we will see how does it depend on those things. Okay, so this brings us to our next topic, that is called types of convection, or free convection and forced convection. And depending on whether it's free convection or forced convection, the H value are different from each other. Okay, so we will discuss free convection and forced convection. Okay, so to understand free convection, so whatever we saw in this wall here, this is actually example of free convection. Okay, So we can take another example. Let's say you have a cup of coffee. All right, this is cup of coffee, which is hot. So what it will do, it will actually transfer heat to the air, right? Or that steam that will have buoyancy, that will actually go up. So this is actually the heat transfer is happening just because of free convection, which is happening just because of the buoyancy. But let's now assume that you add a spoon and you start spinning it, right? What does it do? You are providing extra energy to it, and that's why the heat transfer increases and your coffee becomes colder much quickly, right? And if you take the same example on the wall, so if this is the wall, right, and heat transfer happens from wall to air, and air goes up, so this happens because of free convection. But in same case, now you have a fan here. Let's say you add a fan, right, and it is blowing extra air. So now there is a speed, extra speed that is given to the air, and now the heat transfer rate that's happening. So if this was Q here and this is Q2, so Q2 will be much higher than Q1, right? For the same temperature difference. So if this was T as 40 degree and T here is 20 degree, same here T is 20 degree and T 40 degree, for the same temperature difference, Q2 will be much higher than Q1. And why is that? Because Q2 now has H2 delta T and Q1 is H1 delta T, where H1 and H2 are heat transfer coefficients and H2 is much greater than H1. Okay, that's the heat transfer coefficient. So how do we increase heat transfer coefficient in any medium? We just add external energy. For example, here we are adding in form of fan, right? So when we run fan, we are giving electrical energy, and that electrical energy is converting into mechanical energy, right? And that mechanical energy is actually increasing the heat transfer. And this is exactly any electronic device, let it be in CPU or your laptop. Whenever there is fan, the main aim of the fan is to increase the heat transfer rate. You might think that this is increasing the just like it is lowering the temperature, but why does it happen in first place? Because it is actually increasing this particular parameter H, right? That's heat transfer coefficient. So that is getting enhanced by external energy. Okay, so that's about pre-convection and post-convection. And now to take them in, so couple them together. Let's take an example, and with this example, we will also see how we can use a numerical methods to solve this problem, and also how that can be implemented in MATLAB for coding. Okay. So now let's take one very simple example, similar to what we have just discussed. So let's say this is some solid, some wall which you might be designing a temperature sensor for. So let's say, right, this is a solid and you are designing a temperature sensor. This is temperature sensor, right? And the job of the temperature sensor is to measure the temperature of this inside surface, not the left. So this is a wall, right? In what's happening inside? So this can be furnace, or this can be some pipe flow with hot water or something like that. So it can be anything. Okay, and what you see here, this generally has a TH, that's higher temperature, and this side is air. So T air is always 20 degree, but TH can be greater than T air. But initially, before it gets heated, originally everything is 20 degree, for example. Okay, so let me put it in different words. So there is this furnace which is not working at the moment, right? So Ti Ti here is 20 degree, right? And all of a sudden now furnace starts, or there is some hot water flow outside this wall. Okay, so this part, what you have here, it becomes temperature, it gets the temperature of 100 degree all of a sudden. Okay, so when it gets the temperature of 100 degree all of a sudden, you want to measure that point or that point in time using this temperature sensor. But as we saw before, when you start heating this up, it takes a lot of time, like almost maybe 10 minutes or something like that, to sense that on the other side of the wall, right? Because this wall is actually at 20 degree. This side is at 20 degree. The other side becomes 100 degree suddenly. So it will take a while to get or reach to the other side, right? And we want to model it. We want to see how much time it takes for the heat to transfer from right side to left side, so that this temperature sensor can predict the temperature accurately. Okay, so that's one thing, how much time it takes, and also we will see how accurately it measures. Can this temperature sensor actually measure 100 degree, or it will tell some lower value? Okay, so to understand that, we now let's consider only one small portion of it. So we will consider this one small portion, and we assume that this heat transfer is uniform. So we'll just consider a one-dimensional problem. Okay, this is okay. So that small element, we now stretch it, so it looks something like this. Okay, and somewhere outside here you want to add sensor, and temperature, air temperature is 20 degrees Celsius, and at time t equal to 0, temperature this side was also 20 degrees Celsius. But just at t greater than 0, temperature becomes 100 degrees Celsius. So that is here. Okay, so this is th. So for time greater than 0 is 100 degrees Celsius, and for time just at 0 or before 0 it was 20 degrees Celsius, right? So this gives us the initial condition Ti, that is initial condition is equal to 20 degrees Celsius everywhere, and then we have boundary condition at x equal to 0. Let's say this is x equal to 0, and we assume that the wall thickness is 1 centimeter. So this is x equal to 1. So other side of the wall. So at boundary condition 1, at x equal to 0 is 20. So it is 20 degrees Celsius in the beginning, but now there is a conduction convection boundary condition, which we will discuss shortly. So I should not write this here. It should be conduction convection boundary condition, which we will discuss shortly. But boundary condition at x equal to L, okay, that's on the other side, is equal to, so that tells us temperature is 20 degree, sorry, not 20, 100 degrees Celsius. 100 degrees Celsius for t greater than 0. Okay, so these are few conditions we have, and now we have to write a governing equation, and then we have to discretize it, and then we have to solve it in MATLAB. Okay, so the equation we saw before, now as I said, this is a function of time, right? It is changing with time, and that is why we need to consider this equation dt by dt dx square. Okay, and why we are just considering one term? Because we are modeling it as a uniform flow. So we are just assuming that heat transfer is happening in one direction, not on all three directions. Okay, and it is also changing with time, and that is why this is showing this is the unsteady term, and this is the spatial term. Okay, and what we will do, we have to now model it, we have to calculate the temperature at each location. So let's say here here, at all locations, and also at all times, which are changing. And that is why we need to discretize, or we need to use some numerical methods. We can also solve it analytically, but for today's lecture, we will only solve it using a numerical method. Okay. So let's start with discretizing it. So what we do, we divide this slab into so many small elements. Okay. Where we call the first one as I equal to 1. So this one is I equal to 1. The last one is I equal to capital I. And this one is 2, 3, 4, 5, 6, etc. Okay. And thickness of each element is delta x. Okay. So if total length is L, so I should be L by delta x. And we need to add plus 1 because number of elements is actually 1 less than the points, right? So this should be I. Okay, so what is the total length divided by delta x, that grid size, and then plus 1. Okay, and now we will write this equation for each particular grid. So that's for length scale. And at the same time, we also have this temperature is changing with time, right? We also have delta T. So what we will do, we will model it with a small time increment. We will calculate temperature at very early time, and then we will do some increment in time, like 10 to the minus 4 seconds, something like that. So we'll consider delta T as some value, let's say that's 10 to the power minus 4 seconds. And we will run the code for total T max to maybe 10 seconds or something like that. So total cycles it will run for will be, if you call it n, total cycles, that will be T max divided by delta T. It will give us maybe 10 to the power 5 cycles or something like that. So we will calculate everything in incremental manner. Okay. And now we want to discretize this equation. If you want to do this calculation, we need to discretize it. Okay, so how do we discretize it? This dt by small t, we simply do as, so we will not go into the full details of the discretization, but I will show you just for this equation. Okay, so it is Tn plus 1 by Tn by delta T. So what we are doing, this d capital T, we are discretizing between two different time steps. So what you have as n plus 1 is n plus 1th time step, and n is previous time step. So we have two different time steps. So let's say we calculated some temperature like this in first time step, and in next time steps it gives us some value like this, right? So this value what we have is from this time step, and that value is actually from the other time step, right? And that is why we discretize dt by d small t as Tn plus 1 minus Tn by delta T, where n plus 1 and n, or in other words, n is the time step number, let's say. Okay, and on the right hand side we have d square t by dx square. So this is a little tricky. This is done in a very different way because this is a double derivative. But again, for the sake of today's lecture, we will just consider the discretized temperature rather than going into the full details. And because here we are considering the spatial coordinate, we are not considering the temperature. So we need to consider the ith components. We are not worried about n at the moment. We are going from I equal to 1 to I equal to capital I. And that is why this is discretized as T I minus 1 minus 2 Ti plus Ti plus 1 divided by delta x square. Okay, I hope you are able to follow it. So delta x square, we are, so that is the length, this is a step that the size of the discrete of the grid that we used before. right? Or we defined before, and that is because it's dx square, we use a delta x square, and because it's double derivative, we need to discretize it in this way: ti minus 1 minus 2ti 2 and then ti plus 1. And what are ti minus 1, I and I plus 1? So they are the temperature at different grids. So if this is I equal to 1, this is I equal to capital I, this is 2, 3, 4, etc. So if you want to calculate T here, so that will be Ti, let's say I equal to 3 here. So this right side term, that will become T, so I minus 1 will be 3 minus 1, so that will be 2 T2 minus 2 T3 plus T4 by delta x square. Okay. In this one, because this equation or this term that we have is actually associated with this term, so values for different time steps, and that is why we also associate them with one particular time step, and we will use these values from nth time step. So from previous time step, and we will calculate values for the next time step. Okay. So I hope it is not very confusing, but now we use these two discretization together. So Ti n plus 1 minus Tin by delta T is equal to alpha. You don't remember this alpha term, that's diffusivity, right? And this will be Ti minus 1 n minus 2 Ti n plus Ti plus 1n by delta x square. Okay, so this is our discretized equation. What we are doing here, this is showing us the temperature in different time steps, and this side is showing us the temperature at different grid points. Okay, and if you look at this carefully, this term is for the next time step, right? Next time step. And n here, this one or all these n's, they all belong to the current time step. Okay, so current time step is something that we have already calculated, and now we will use it for calculating the next time step. And that is why if you take everything which are associated with nth time step, we can actually calculate n plus 1 time step. So we will take we will keep Ti n plus 1 on the left hand side and put everything on the right hand side. Okay. All right. So what do you see here? What we have in the right is actually all nth time step, right? And this one is n plus 1th time step. So if everything on the right is nth time step, they are generally known parameters. We have already calculated them. And because now we have calculated them, we know what is these, we know we have defined these things, we know this, we know this, we know this, we can actually calculate this value. Okay. But there is a problem. There is a problem. Problem is at the boundary condition. So as we saw this is I equal to 1, this is 2, this is 3, this is 4, and it goes up to capital I minus 1, and last one is capital I. So this one works very well. This thing works very well for I equal to 2, 3, 4, etc. Why? Because let's say we want to calculate T2n plus 1 term, right? There we know T2n plus alpha delta T by delta x square, then Ti minus 1 should be T1n minus 2n plus T3n, right? Because this I plus 1 is, at the moment we are considering I equal to 2. So this one should be 3, this one should be 1, and this one should be 2. And that is what we have: 1, 2, 3, and then all nth term. And then we calculate n plus 1 term for I equal to 2. What will happen when we want to write this equation for I equal to 1? That will be T1 n plus 1 is equal to 2 T1 n. That is all right. Then alpha delta T by delta x square. Now problem comes here. It should be I minus 1. And we are considering I as 1 already. So it should be T0. And as we all know, there is no T0 term. This term in T0 does not even exist. Sorry, not T0. I0 does not even exist. And that is why this equation what we have, it cannot be applied for I equal to 1. We need to write a separate equation for that. Okay. Likewise, when I is equal to capital I. So when we are at this term, the right side term, there also that doesn't work. Why? Because if you want to write it for T capital I term, we have T capital I n alpha delta T by delta x square. This one will work fine, that I minus 1 n minus 2 I T I n plus T I plus 1 n, right? In this term does not exist, right? Because we have grid points only till I. The I plus 1 does not exist, right? And that is why this equation does not work for I equal to, sorry, a small I equal to capital I. It does not work. And that is why the equation that we saw before, now let's use a different color. We have been using this. So this equation works only for I equal to 2 to I equal to capital I minus 1. Okay, it does not work for all of them. And that is why we need to apply three different conditions. One for I equal to 1, one for I equal to 2 to I minus 1, and one for I equal to capital I. Okay, so for this one, we have that equation that we saw, energy heat equation. We will use the heat equation. Okay, and for the right side one, we already know that temperature here, or we already defined somewhere here, right? Temperature is constant. So here, right, we saw that temperature is already defined. That is actually T equal to 100 degree. So we don't really need to calculate that because that is kept fixed at 100 degree at all times. And that is why this one we don't really need to worry about. So n plus 1 at capital I is always equal to 100 degrees Celsius. We don't really have to calculate it. This is already calculated. And this one we already saw the discretized equation. Now we need to find the condition for I equal to 1 for the first one. So here we will use convection, conduction, convection boundary condition. Okay, so let's see what's happening here. So as I said, T air is 20 degrees Celsius, right? And there is, this side is T equal to 100 degrees Celsius, right? And now slowly heat transfers this side, and there is a heat transfer from this wall as well to the air, right? Because this is also getting heated up slowly. If it was 20 degree in the beginning, this might be 30 degree, this might be 40 degree after some time, right? It can be of any temperature. So heat transfer will happen, and that heat transfer will be because of convection. Convection, and this heat transfer is happening because of conduction, right? And at this wall, at this point, convection must be equal to conduction, where at x equal to 0. Okay, and how much is the convection? We talked about that before. Q convection is equal to H A T. Let's say now we have already defined this that as Ti, right? So we divided this into like I equal to 1 and I equal to capital I. So this is 1, right? So we call it T1. Okay, so T1 minus T air, that is the heat transfer that's going from the wall to air. Okay, and then we have Q conduction, and that must be equal to Ka dt by dx, right? And that is coming from, let's say if this was, use another color, if this is I equal to 1 and if this is I equal to 2, so this Q is coming from I equal to 2. So this delta T must be T2 minus T1, right? And this should be equal to dx, should be equal to our grid size. All right. So we saw this is heat transfer due to convection and this is heat transfer due to conduction, and they both of them must be equal to each other for doing the energy balance, right? And that is what we have. Ha T1 minus Ta. So Ta is known, we know what is Ta, that's 20 degrees Celsius. We don't know T1. T1 is something we need to calculate. Is Ka T2 minus T1 delta x. And now I got rid of negative term, so don't be confused with that. There was this negative term which I got rid of because I did T2 minus T1. If I did it T1 minus T2, then I would have to put the negative term. All right, so now what we will do, we are trying, remember we are trying to calculate T1 here as per this one. So we want to calculate T1 because T2 to Ti minus 1 can be calculated using this equation, and Ti capital I is also calculated. So this is known, these two we can calculate, I mean from T2 to Ti minus 1, and this one is not known, and this is what we are trying to calculate here. So we will take T1 to the left and everything to the right, and that gives overall balance gives us HTA plus K T2 by delta X divided by H plus K delta X. Okay, so this is how T will be calculated. And remember, we have steps. So we are actually trying to calculate for some particular time step, and let's call it we are calculating for some n plus 1 time step. And now we assume that T2 is already calculated for n plus 1 time step. So we can simply use T2 value for that n plus 1 time step. And everything else in this equation is already known, right? We know H value, we know Ta value, delta X we have defined, K is known, and all these are known. Okay, so I believe we have now set up the problem completely. Let's do a revision quickly, and then in few minutes from now we will switch to MATLAB. So we have this as I keep making this mistake. I equal to 1, last point is capital I, and then we have all the grids which goes from 2 to capital I minus 1, right? So when I equal to 1, we have T1 as HTA plus KT, it should be T2, yeah, T2 by delta X, H plus K by delta X. Okay, and for I equal to 2 to capital I minus 1, and this we should not forget to put n plus 1, and then Ti n plus 1, how much was, what was that? Ti n plus alpha, it should be delta alpha, sorry, alpha delta T by delta X square, right? And it was Ti minus 1 n minus 2 Ti n plus Ti plus 1 n, right? If you remember, this is what we had got already. Let me show you once again. I think somewhere here, this one, this equation, right? In the last point, Ti was already known. So I equal to capital I, that is T capital I n plus 1 is already known, that is equal to Th, that hot temperature, and is equal to degree Celsius. Okay, so now we have got equations, discretized equations or boundary conditions for all points from I equal to 1 to I equal to 2 to I minus 1, capital I minus 1, and then capital I, right? So this problem is complete, and now we can write a MATLAB code for this. Okay, but there is one thing that you need to know. If we want to make, because now we will be running this code and we will be defining a small delta t delta x, many times codes don't converge, right? They diverge from the values we want to get. They don't give you the right value. So in that case, we need to define some criteria. So this term what you have, let's call it beta. So beta is alpha delta t by delta x square. So for convergence criteria, this term must be smaller than 1. Okay, this is convergence criteria. If this is not satisfied, then our equation, our model can give us very results can actually diverge from what we want. It will not give us the right values, and that is why this condition must be satisfied. So alpha is actually known value. We will define alpha, and I think we can actually consider alpha to be, for a realistic problem, we can consider alpha to be 0.2 centimeter square, sorry, centimeter square per second. And then we also need to define h and k. So again, for making it more realistic, we can actually consider h as 0.01 watt per centimeter square Kelvin and K as 0.1 watt per centimeter Kelvin. Okay, we will use these values, and based on this, if you want to satisfy beta, we can define some delta t and delta x. But for our code, I think we will define delta t as 10 to the power minus 5, which actually is quite a small, but it's important to have very small number. Okay, and delta x as 0.01. Okay, so these values are set. Okay, and we also got all the governing equations, and now we can write them in MATLAB. Okay, and there is just one more thing I would like to do before we go to MATLAB, because once I go to MATLAB, I'll not be able to edit it here, and that is asymptotic condition, which also we will see. Asymptotic condition. So what happens? Let's say this wall gets heated to 100 degrees Celsius all of a sudden, and outside temperature is 20 degree, right? This is what we have been discussing all the way. So when you continue, so in the beginning we will see some temperature gradient. Slowly it will start heating up. The temperature here maybe after some time it may become 30 degree, it may become 40 degree, and then it may reach 90 degree, etc. But after a long time, maybe 10 minutes, after 1 hour, we will see one single temperature gradient. It will not change anymore. Okay, we will see that one single temperature gradient where this side temperature will be fixed at some temperature. I mean, T1 will be constant, Ti is already constant, that is 100 degrees Celsius, and T air is constant. So after a long time, T1 actually becomes constant. It doesn't change with time anymore. Okay, and to be able to find that, and that we will see in MATLAB, but to be able to find that, we again apply these conduction, convection, boundary condition. And what was that? We, just to remind you, that was this equation. Yeah, this particular equation. Okay. So that if you want to calculate this is T1, so this will give us H T1 minus Ta should be equal to K delta T by delta X. And now in long time limit, we can actually define delta T as for the whole block rather than just for a small delta X, because there is no variation anymore. So we can define that as TH minus C1 divided by L, total length of this block. And that if that total length is L here, and right, so this is L, so we can actually define that as total block, and we don't really need to worry about this. So what will happen in that case? H T1 minus Ta is equal to K TH, which is actually 100 by L. Okay, and this gives us the temperature T1 as HTA plus KTH by L divided by H plus K by L. Okay, so this is what after long time T1 will become, and it will be a constant number. So this is that's why we are calling it asymptotic value, which after long time it becomes constant. Okay, and we now know the values of all other parameters. We have defined H, which I believe is 0.01, K is 0.1, in L we assume that that's 1 centimeter, that was the thickness of the block, if you remember, right? And TH is 100 degrees Celsius and TA is 20 degrees Celsius. So if you put all these values, I believe the T1 we get is 92 point. I did this calculation before, so that should be this value. Okay, so this is a long time temperature, but before we reach 92.7 degrees Celsius at T1, we need to do the transient calculation. So this is one thing we will discuss maybe in the end, and this is the error that your temperature sensor will show. So we remember we were trying to design a temperature sensor here, right? Sensor, and we said that this becomes T equal to 100 all of a sudden, where this side temperature is 20 degree, and after how long this sensor will be able to sense this temperature T100? So the correct answer is it will never be able to sense that temperature. Okay, even if T goes to infinity, it will never reach that temperature. But what maximum temperature it will reach? T1, let's say we call it TS for now. Instead of calling T1, we call T sensor, which is actually equal to T1. Maximum temperature that it will show is 92.7 degrees Celsius. Okay, so inside temperature or other side of the wall temperature is actually 100 degrees Celsius, but maximum temperature we can read by a sensor is only 92.7 degrees Celsius for this particular case. Okay, and that is why when you are designing this sensor and we are trying to measure this measure temperature, if you are aiming to get 100 degrees Celsius, that you will be wrong. You can only expect to get this maximum temperature, and beyond that it will just become kind of static. It will not show any further temperature. Okay, so we have to now check another. So this is first thing that we want to check, what is that delta T that we get. So this is basically we get a temperature difference of 7 degrees Celsius, right? So or to be more precise, it should be 7.3 degrees Celsius temperature difference, or you can even call it maybe error of measurement, because you will never be able to get 100 degree, but you will be able to get this one. So this is the error that you will get in your measurement. And second is how long it will take. It will take to reach 92.7 degrees Celsius, right? It is never reaching 100, but let's see at least how quickly it reaches this temperature. And to do that, we need to do some coding or some modeling. So now we will go to MATLAB and we will solve this particular problem that I showed. This one, right? We have got the conditions already, everything is ready. We will go to MATLAB and we will solve it. Okay, so actually I have written this code already, so you don't really have to worry about it. But let me open that document as well. Right, so okay, so this document is updated. So now let's look at this MATLAB code that we have. Okay, so we defined many things, starting with the thickness of the slab. So that is 1 centimeter. Okay, that is equal to 1 centimeter. That is thickness of the slab that we are trying to model. Okay, and then we define delta x, that is 0.01 centimeter. Okay, 0.01 centimeter. So we are actually dividing the complete slab into 100 grids. Okay, total 100 grids, and then we have T max, that is total time, maximum time we want to run the code for. Want to run the code for. Okay, then delta t, that is the time spacing between each increment. Okay, so that is 10 to the power minus 5, or let's call it delta time. Okay, and then that is heat transfer coefficient. I don't think I need to write them everywhere, but heat transfer coefficient, and then thermal conductivity. Okay, and then alpha is thermal diffusivity. This is diffusivity, right? And then TA, I have written these as T, let's call it TH. Okay, so TA is air temperature, right? Air temperature. We are defining everything one by one because that's important. And then this is initial temperature, which is actually equal to air temperature. Okay. Okay, and this is temperature. Let's call it heated temperature. All right, and then you just saw this equation, right? How we calculated this T asymptotic, this one, which I'm calling T1, that's asymptotic temperature, and that maximum we got was 92.7, and we will also see that here. Okay, so that is T asymptotic, and I use the same formula, and then I'm defining n is the total number of time steps. So total T max, that is time max, if you remember, that is 10, total 10 seconds we will be running the code for. Okay, so this, I think I should also write this here, that's in seconds. Okay, and this is also in seconds. Okay, so that is total number of time steps, the increment that we will do, and then x is number of grid points, that is total 100 plus 1, because the total length is 1 and we are dividing them by delta x, that delta x is 0.01. Okay, so that I'm sure you remember, but if you don't, that should be this thing, this one. Okay, I equal to 1 to I equal to capital I. All right. Now let's go to MATLAB code again. And then we have capital I, T. So we need to define the initial condition that capital T, that's temperature everywhere, is Ti, and Ti is 20 degree, that we already defined here, right? Then beta, you remember beta, that is this convergence criteria, right? These convergence criteria, which should be smaller than 1. Okay, so that we have defined beta here. And then T plot. So that is something that you don't really have to worry about. I just wanted to make it easy for plotting, but main part comes here for. So I defined 2 for loops here. Okay, 2 for loops, one for time. So this for loop is for time, for loop for time increments. Okay, and this one is for loop uh, for the grids, let's say, for the grids. Okay, so, and this is the equation that we are trying to solve. So you remember we have 3 different equations, one for time equal to 1. Okay, let me come here, and that will make it easy. Okay, you can see this. We have separate conditions, right? Different conditions for I equal to 1, then 2 to I minus 1, and capital then for I. And we will define these 3 separately. So we start with I equal to 2 to I minus 1. So T new is basically n plus 1th term. Okay, T new is n plus 1, sorry, n plus 1th term. Okay, and T is nth term. All right. So that's T new, and T new is n plus 1th term we are calculating. And if you remember the formula, we have this T nth term for ith point, then beta, and then you see here this I minus 1 to Ti plus 1, etc. Okay, so this is for I equal to 2 to I minus 1. All right, and then we have fixed condition for capital I. When I is equal to capital I, that's equal to Th, and Th is 100 degrees Celsius, right? That is fixed. And then T new at I equal to 1. So the for the left boundary condition. So here we apply that convection condition, boundary condition again, and we get this criteria, right? So from these 3 lines, you can see we have calculated T new, that n plus 1th term for all different I equal to 1 to I equal to capital I. So that I equal to 1, I equal to capital I here, and then I equal to 2 to I minus 1 here. So everything is there. All right. So once this part is done, so that is calculated for that particular iteration, and now we go to the next iteration. So by next iteration, I mean next time step. And when we go to the next time step, I update that T with T new. Okay, so I calculated T new, but for the next time step, that T new has become T old. Okay, so now this n plus 1th term has become n. So that T is updated, and this actually will be going back to here. So again, you don't have to really worry about this part. This is something I did just for the sake of plotting, but main concepts are here, these 4 lines. Okay, so this T is getting updated every time steps, and now this whole thing will run for n equal to 1 to n minus 1. So 1 to maximum number of so for the maximum time limit. Okay, and this is the way I'm plotting. So I actually get this temperature for some particular time steps. I don't want to save in my computer for like more than 10,000 time steps. I save them only for 100, and that is what I'm doing. So if I run this code now, it's already written, and if I run it, you will see how we get results on this MATLAB. Actually, just 1 second. How to move this screen? Okay, I think now it should. Okay, so are you able to see my screen? So these are two figures that we have. See, so what we are plotting here, temperature, this, what you see at the right is temperature on the right boundary and temperature on the left boundary. So temperature on the right boundary is actually 100 degree, right? That is what the fixed condition we applied. And what you see here in the dashed line, in the bottom, right, dashed line, that is at 20 degrees, 20 degrees Celsius at time t equal to 0. Okay, and as time progresses at different time steps, this is how the temperature is evolving. So this right boundary becomes equal to 100 degree immediately, but everything else actually increases slowly. So what you see in these curves, different curves, actually they are increasing in time at different time steps. So in early time, left boundary has reached, so T1 has reached 36 degrees Celsius. In others are greater than that, but slowly it becomes 100 at the right boundary. And later in time, we have run the code for 10 minutes, 10 seconds, you remember. So the last one, the red one, is actually presenting you the results for t equal to 10 seconds. And you can see how the curve has become a straight line. It's not a curve anymore, and that is not changing. And that is what you see. These green lines, they are very close to the red line, right? And the reason is now the change in temperature is not much. It has become almost asymptotic. Okay, and that becomes clear here. If you look at this figure, right hand side, here I'm actually plotting the temperature of the left boundary. Okay, that where is that? Yeah, at point I equal to 1, and that is the temperature that is sensed by the sensor. Okay, so that temperature, so this temperature that will be sensed by the sensor. So at time t equal to 0, obviously everything is at 20 degrees, so temperature sensor tells you 20 degree, but as time progresses, sensor tells you different temperature. At 1 degree, after 1 second it tells you around 30 degree, after 2 seconds it tells you around maybe 45 degree, after 4 seconds it tells you 70 degree, but only after 7 or 8 seconds, or maybe after 10 seconds, it has almost reached this asymptotic value that we derived, you remember, 92.7 degrees Celsius. Okay, so it takes almost 10 seconds for the sensor to tell you the right temperature of what is happening on the other side of the wall. Okay, and only when this reaches this asymptotic value, so this curve, this solid curve, it will never go beyond this dash curve. The maximum value we can get is 92.7 degree based on our calculation. Okay, and for that asymptotic state, this the red curve that you see, a red line, that is the temperature gradient we will get. Okay, so the temperature gradient will be, I mean, or temperature at each point will be constant. Okay, once the asymptotic state is reached, but until it reaches the asymptotic state, the temperature will continuously increase. Okay, until it reaches that maximum value. So two things which we wanted to see from this analysis is, when you design a sensor, right, our main aim, let me go back to this problem that we, when we started discussing. uh, Okay, so I don't think I wrote that, but you remember we discussed two things. First, we wanted to know how long it takes, and second, what is the error. Okay, so error, as we saw already, is around 7.3 degrees Celsius. Sensor will never give you the right value, and even to reach this temperature that it shows, that's 92.7 degree, it takes almost 10 seconds. Okay, so this is one very simple example where we included the concepts of both conduction and convection, and we also did discretization, and we did this coding in MATLAB, right? And we tried to solve it. So based on this very simple coding, just maybe just few lines coding, we are able to see how these temperatures are obtained, or how the heat transfer is happening, or what kind of behavior we can expect or how long it will take for sensor to sense the temperature. Okay, so this is a very simple example, but obviously in case of complicated electronic machines, there is not just one component. There are obviously hundreds of components, and they have different behavior based on temperature, and they are very complicated to. It is very complicated to study them individually, and that is why it becomes very important to consider computer modeling, where you put different components, different parts, and you put their boundary conditions, and then you try to run codes. And for that, obviously, today's lecture, it's not feasible to consider everything, but I hope you understood what exactly happens, or how do you model a heat transfer problem in computer. And this we did based on just one dimension in length and then in time, right? But when it becomes two-dimensional problem, or most of these electronic machines are three-dimensional problem, it becomes very complicated. And one very important thing is convergence. Many times it doesn't give you the right value, it gives you some random values, some wrong values. So it is very important to do this analysis or modeling very carefully, step by step, so that you are able to get the right result. And I think with that, I finished my lecture. I hope it was useful for all of you to understand what exactly goes inside a modeling, and hope you will be able to use some of these basics in your own teaching or analysis, or any modeling you do in future. And with that, I would like to thank all of you for attending this lecture. Thank you. And if you have any question, obviously you can ask me.
Sir, can we write the second order differential equation del square t by del x square term? You have separated the components. Uh,
Right.
can we directly write that term in MATLAB? Del square t by del s square.
So MATLAB has its own, inbuilt solvers, and you don't. I mean, today's lecture was more to let you understand how do we discretize it. But MATLAB, yes, there's for example, for OD there is OD 45, etc., and for PD as well there are many solvers which I'm not remembering, but I have used in the past. So you can definitely use direct inbuilt solver in MATLAB.
Sir, actually, I wanted to ask. Chunendra sir separated del square t by del x square term into ti minus 1 minus 2 ti. It is a standard
Right.
derivative, second order derivative.
Right.
I'm asking, can we write directly?
So so you also, I think you are also talking about implicit and explicit methods, is it?
Yes, sir. Yes.
Yes. So what I did today was I completely use an explicit method, right? So when you use use an explicit method, you use values from previous time step to calculate values for the next time step, and that
Okay,
makes
okay.
it much easier, right? And that is why for n plus 1th term we were using values from nth terms,
Okay.
nth time step. But there is another, and that is obviously more precise. If you use values from nth term, sorry, n plus 1th term to calculate values for nth term, you just need to do some uh, a trial and error type method. But it is possible, and that is called implicit method. Okay, and what I used was explicit, and there is another thing called semi implicit, where you use half values from previous time step and half values from the new time step. So when you
Okay.
use, it's just that it
Yes, yes,
increases the
sir.
number of iterations you want to use, but otherwise, yes, uh, that is possible, and that's an excellent question. Thank you. Yeah, not just OD, there is even PD solver. So, like for OD, there is OD 45, which I have used extensively. But even for PD, there are several PD solvers, which I haven't used much, but I do know that there are PD solvers where you can just put these values like value of beta, etc., and then it will give you the results. Yeah, so there were some comments. For example, there is one candidate from chemistry department, and he said he understood what we taught. So I'm glad it was helpful and you are able to understand what we taught. Thank you.
Sir, I have one more question. This is beyond this topic. Is there any MATLAB code exist for solving transcendental equation?
What equation?
Transcendental equation.
Okay. Maybe I'm
Transcendental
not familiar with
equation
that.
to find zero
Yeah, you
field.
can use F solve. Function solve, F solve. F solve is a inbuilt MATLAB function, I think, which did some least square minimization to find your actual value. So I have used F solve. So F solve can be used to solve transcendental equation or implicit algebraic equation kind of thing.
Minimization also can be possible.
Minimization also can be possible. So F solve and related functions are there, which are very powerful actually.
Okay,
So
sir.
I have used that for some data fitting purpose and things like that. So I know it. That
Thank you,
for
sir.
algebraic equation, not for differential equation. So for algebraic equation kind of thing, which you so you can also feed some experimental data when you want to feed some experimental data. Also, you have some equation, you have some data point and some parameters. So changing the parameter, it will calculate. So it can handle up to many parameters. So I have used up to like. Yeah, it takes the parameters as like matrix and things like that. And if you try to write the code very efficiently, like in matrix form and into reducing the number of for loops, everything writing it. So MATLAB has lots of functions that do very beautiful things with matrix entries and things like that. So yeah, sometimes if you learn those things, then your code, I think, runtime increases. So I was just curious. In MATLAB, there are many inbuilt functions which does beautiful things with matrices, right?
Yes, yeah.
Yeah. So if you use those functions, I think your runtime increases a lot than using some kind of nested for loops and things like that.
Yeah, exactly. There are many things. In fact, for example, you want to divide a matrix by another an array. So many times you start writing a code for it, but there is simple, you divide
Yeah,
matrix
yeah.
using backslash by
Mm-hmm.
an array. So maybe many people don't know that and they start writing code. And if you use that one line, inbuilt function, that gives you the results very quickly. So apart from that, I think there are many inbuilt functions which make the code much faster. It's,
Yeah, yeah. That was, I think, the question.
yeah. And as per the suggestion, actually, one candidate suggested, right? We can arrange this session for just for MATLAB, where we can
Yeah,
discuss many
yeah.
different
Sure,
things.
sure,
And I'm
yeah.
sure MATLAB is something very useful, and it's not just used by people in, let's say, fluid mechanics. People in every department they
Everyone.
use
Yeah.
MATLAB now.
Every department, every engineering,
Yeah,
science, every department, I think they use MATLAB
yeah,
nowadays, right? Yeah.
right, right.
So, yeah, thank you.